So now we will look at a description of the changes in magnetization, and this will bring us to a full description of the changes in the longitudinal and transverse components. What we have to do, we have already seen in the previous lectures, in the previous weeks, we have seen the Larmor equation, which describes the precession of magnetization around either a static magnetic field or a rotating magnetic field like the B1. Now what we have to do here is we just have to add the terms in the differential equations for relaxation, that is T1 and T2. So for the Z magnetization, we will have this term, that's along Z. For the X magnetization, we have this term. And for the Y magnetization, we have this term. Now, this is a fairly complicated set of equations here. As you can see, they're coupled differential equations. But if we look at this as a whole, this expression here, this is nothing but the vector product of gamma B with M. So this describes the precession of the magnetization around the magnetic field B. And here B is a general term, a general vector. Now we have the relaxation along Z that we have introduced this week. So we have the change in magnetization along Z, change in magnetization along X and Y. So these are the relaxation terms. And this gives us the full set of differential equations, the behavior. So we have, on one hand, we have precession around B, that's these terms here, and we have relaxation now incorporated. And these equations, these three equations here, are the Bloch equations. They're named after a Swiss physicist, Felix Bloch, who was awarded the Nobel Prize for his discovery of the nuclear magnetic resonance effect. He was awarded the Nobel Prize in Physics in 1952. If we substitute the term for the rotating reference frame, so we'll substitute the big omega, which is given by minus gamma B0 plus omega RF. Then we obtain these equations for the term. That's substituting these three equations with this term. And this is the rotating reference frame, or in other words, it's gamma B1 plus omega in the rotating reference frame that rotates with the B1 cross M. So that would be in the description in the rotating reference frame. Now, what characterizes the basic NMR signal? We'll start out with the transverse magnetization, and here I'll describe it as a complex function. So the transverse magnetization in complex terms is given by the transverse magnetization at time 0 times e to the minus I omega t times e to the minus t over t2. This is relaxation, this is precession. Here we're using the complex notation, we're using the real part, for example, to represent the x-axis and the imaginary part to represent the y-axis. And what does this signal look like, this expression? This is the x component. The envelope, that is the amplitude decays with t2, that means the envelope decays with t2, and we see oscillations here in the real part, that's the cosine omega t term. Likewise for the y term, that would be the imaginary part of this equation, has a similar function, except it's sine omega t in this case, but it has also the t2 as the decaying amplitude, the t2 effect. For the longitudinal magnetization, and here I'll just stick to the case where we have a 90-degree full excitation, so the magnetization has been flipped into the transverse plane, then the Z magnetization, the longitudinal magnetization, is equal to m0 times 1 minus e to the minus t over t1. So in the end, what we have is a complex description of the motion. We have the z component, which recovers towards m0. We have the x and the y component, which basically together means that the transverse component rotates in the transverse plane according to the Larmor equation and also decays exponentially. So this is could be described by a behavior like this, and this is fairly complicated. So if we look at the Z magnetization, it builds up in an exponential function. So it goes from 0 to m0. And this, how fast it recovers to m0, is described by T1. So we have the equilibrium Z magnetization like this. We'll start out essentially at 0 magnetization. And then what happens with time is that the Z magnetization recovers with e to the minus t over t1 towards m0. That's what the magnetization vector will do over time. Now, if we look at the transverse component, mxy, I'll here not distinguish between x and y, I'll just take this as the transverse component. Then this component decays while the z component increases. Of course, mxy precesses depending on the choice of our rotating reference frame. Okay, so we have also a condition here that we can never exceed the equilibrium magnetization m0, and this is a constraint, that is that if we look at the norm of the vector, the total magnetization vector, it cannot be bigger than m0, and this typically implies that T2 is not bigger than T1. It is typically much smaller, but certainly it does not exceed T1. Now, I want to give you an example. This is a preparatory example for what is to come in next week. And this is how can we be sensitive to T1 changes? Or how can we measure T1 changes in precisely? And here we'll consider a so-called multipulse experiment. So the experiment is fairly simple. An RF pulse, that is a B1 field, is applied every TR seconds. So here is our scheme. We apply this every TR seconds. So here's the time TR. Then we have a flip angle alpha applied here, and we'll set this to 90 degrees. And what this pulse does, it converts the Z magnetization to transverse magnetization. And then the signal is measured. So at the beginning, the signal is proportional to the Z magnetization, and therefore it is sensitive to T1 effects. So now we'll take the basic differential equation that describes the behavior of the Z magnetization. We have the recovery to m0, and we have this starting magnetization m0, that m of time 0, that decays with T1. At time 0, we can say that the magnetization, the Z magnetization, is m0 cosine alpha. And then we can write this in this form. That is, basically, we are using the fact that we have used a 90-degree pulse here. So m0 cosine alpha, since cosine of 90 degrees is 0, then we have this term is 0, so our Z magnetization is just this term here, which is written here again. So if I express this now as a function of the repetition time, so we repeat our 90-degree pulse every TR seconds, then our magnetization, Z magnetization as a function of TR, is given by the equilibrium magnetization times 1 minus e to the minus TR over T1. Now here what is crucial is we have an effect of T1 as well as an effect of, the same holds true for T2, but the effect of T1 on the signal depends strongly on how it is measured. So let me give you the example here. If we take a short T1 component and we measure every 500 milliseconds, we get the signal intensity that is like this. If we have a long T1 component, but we measure with 1.5 seconds TR, we get the same pixel intensity. So unlike the CT units, the CT numbers, the Hounsfield units, in an MRI, we cannot attribute a signal intensity in a pixel to a specific value of T1 or a specific biophysical mechanism, because we need to know on how this has been measured. So in this particular example, if we had measured at 1.5 seconds, this component will give the same intensity as if we had measured at 500 milliseconds for a short T1 component. So this is essential here, that the pixel intensity as such doesn't have a direct biophysical interpretation. Now, if we are doing this multi-pulse experiment, so we apply a 90-degree pulse every TR second, at what point would we be most sensitive to changes in T1? And for imaging that's important, that would give us the maximum contrast. To approach this, we will use the error propagation calculation that I introduced in lesson 1 of part 1 of this course. The same procedure here applies. So first we calculate the derivative of the Z magnetization with respect to T1. This just tells us how strong does the Z magnetization vary if one were to vary T1. So where is the Z magnetization? How much does it vary in response to variations to T1? So that's just the derivative of this term with respect to T1, and this is the expression that we obtain. And we'll call this function big F. Of course, we know if we measure with TR essentially equals 0, the magnetization cannot recover, so it will be essentially 0, so we are not sensitive to changes in T1. And if we write 5 times the biggest T1 of that is present in our tissue, then everything has recovered to M0, and we're again not sensitive to changes in T1. So somewhere between 0 and infinity, for the time t, we have a maximum of this function. And to find the maximum of this function f, we'll take the derivative of f with respect to the time t, which is here the tr. We'll set df to dt equals 0. We want to find the maximum. We do the chain rule for derivation. So that's what we are interested in. And then we obtain this expression here. If we simplify what we've obtained here, this is not 0, this is not 0, so only what is in brackets can be 0. And t is equals the optimal tr if the optimal tr is equals to t1. So this is a not surprising result. We have seen similar things. We're always dealing with exponential functions, and typically the change in the decay constant, or here the T1, is optimally detected if we measure at a experimental parameter that corresponds to this decay time, or the T1 here. So in other words, if we have a rough idea what the T1 is, we should be setting for a series of 90-degree pulses that we apply every TR seconds, we should be setting this TR to roughly T1 to be most sensitive to changes in T1. Okay, and here is a message that is dear to me that I want to stress. The intensity in our images, in the images, the MRI images that are being measured, depend strongly on the relaxation, but in a way that depends strongly on how this signal intensity is being measured. So let's look at the transverse component. We have transverse magnetization. This is cerebrospinal fluid. We have gray matter, white matter, and fat. And we can see for CSF, cerebrospinal fluid, which contains very little cell membranes, very little proteins, the T2 is very long. It's about 1.4 seconds in this example. Gray matter is at 100 milliseconds and white matter is at 90 milliseconds. And then we have fat here. So 37% of the decay signal gives us the T2 here. If we look at now at the recovery, here's a 90-degree pulse and the recovery, then fat goes the fastest, white matter goes second fastest, then gray matter, then CSF, and CSF here in this example has a T1 of 2.5 seconds. So what we see here is now typically we would do a T2 weighted image. If we want to see changes in T2, we would wait a certain time after the excitation pulse and detect the signal. Now CSF will be the brightest because it has the longest T2. It has very little protein in it, so it has long T2. Conversely, CSF has long T1, but here we're reducing the waiting by waiting not the full time. We're waiting a shorter time than full relaxation. So actually the signal from the cerebrospinal fluid will be lower compared to the signal from gray matter and white matter. And so even though it has a long T1 and a long T2 in T1 weighted images, the CSF will be dark, and in the T2 weighted images it will appear bright compared to the other tissues. So let's look at an example here. We have on the vertical axis we are plotting the time after excitation, and the TR on the horizontal axis. And so we have a very long TR. Here we go from 30 to 160 milliseconds. Look at the light eye bulbs, which are primarily just water, how bright they get with a longer echo time, time after excitation. As we start reducing the TR, we're starting to have increasing effects of T1, and we're starting also to see that the images are getting darker. That is a consequence of the not being over here, but being more and more closer to this situation. We're here at 800 milliseconds, and here is 200 milliseconds. We can clearly see the fat here becoming bright at short echo time and short TR. The fat is becoming bright, the CSF here is dark, the eyes are dark. That is consistent with these values here. And what is also important here is a good choice of parameters allows to depict certain pathologic conditions. A bad choice of parameters is detrimental to detection of any signal. So if one is to choose a long TE, time after excitation, and a long TR, then we are basically seeing no signal, and that is not a good choice. So in order to interpret MRI signals, one has to know the experimental conditions that are being done, and this is one of the reasons why MRI is such a complex technique to use in clinical practice, but it is also an advantage because we have a lot of mechanisms and means to manipulate image contrast. Now, I want to conclude this week's lecture with a summary on magnetic resonance. What do we know so far? So, we have established 2 weeks ago that last week we have established that we need a magnetic field B0. This establishes a equilibrium magnetization M0 that is parallel to the z-axis, and this equilibrium magnetization increases with the number of spins in the voxel, it increases with the static magnetic field B0, and it increases with the gyromagnetic ratio gamma. So that's one thing that we need. We need to be in a strong magnetic field to have an equilibrium magnetization. Then we need a RF field, B1, which is typically applied on resonance, that is close to the Larmor frequency omega L. And this B1 field allows us to tilt the magnetization into the transverse plane. So we're tilting the Z magnetization into the transverse plane. Here the plane is in XY. The signal detection process of magnetic resonance imaging is done by precession. We're looking at the transverse component of the magnetization that precesses around the magnetic field B0. That is the detection process. Then we have established this week that we have relaxation for T2 that decays and for T1 which builds up. So we have an exponential decay of the transverse magnetization and an exponential return of MZ to M0. That's described by T1 and T2 relaxation. These time constants T1 and T2 reflect the molecular environment in which the molecule finds itself, and they are a major source of contrast in MRI. So now some take-home messages. In MRI, we can only detect mobile spins. So typically, of major interest here is water. Immobile nuclei that are part of a molecule that's immobile are not detected. The equilibrium magnetization reflects the number of nuclei and thus the water content in tissue. Now, water content typically varies between 70 and 100%, or 70 milliliters per 100 gram to 100 milliliters per 100 gram in our bodies. And so it is actually not a good source of contrast. To detect tissue contrast, we rely on differences between T1 and T2. Those T1 and T2 differences, how they manifest themselves on the image contrast, depends strongly on the experimental parameters. Example that we have seen are RF pulse timing, or generally pulse timing, and another example here is the flip angle alpha by which the magnetization is tilted into the transverse plane. So these are the key messages. This is what we have so far dealt with magnetic resonance. Next week we will talk about spectroscopy, and this link makes a link between MRI and the chemical applications of magnetic resonance.